Dear students, continuing with the photochemistry of organic compounds, in this lecture we will discuss about cis-trans isomerization, which generally take place in case of alkenes. So if we take the case of simple alkenes, they absorb through pi star transitions, and lambda max is generally less than 200 nanometer. And different types of electronic states, if we see the simplest of the molecules, that is ethylene, then the first excited singlet state, that is between pi and 3s orbital, it requires 164 kilocalories per mole of energy to get the electron excited from ground state to the first singlet excited state. Similarly, in case of ethylene, we require 175 kilocalorie per mole of energy to excite the electron from ground state to the second excited singlet state, that is pi star transition. And if we are to excite the electron to the S3 state, that is second excited singlet state, then we require 180 kilocalories per mole of energy. And similarly, if through intersystem crossing the singlet states, they are to be converted into triplet state, then this much of energy is required: 101 kilocalorie per mole for T1, that is first excited triplet state, and for second excited triplet state we require 150 kilocalories per mole of energy, and this transition is a Rydberg transition. Now, as far as intersystem crossing is concerned, that is conversion of singlet state into a triplet state, the energy required in case of alkenes is generally very high, that is of the order of 70 kilocalorie per mole in case of ethylene. So that is why because of this high energy, the intersystem crossing from singlet state to the triplet state is a slow process, and this is also not very efficient process because of the high energy requirement for this conversion from singlet to the triplet state. So because of this, the direct irradiation of alkenes, this generally gives us products mainly through singlet excited state of reactions. And for triplet state reactions, we require the use of any sensitizer which can lead to sensitize the substrate alkene, so that it can be converted into a triplet state easily instead of intersystem crossing. Then some general characteristics of these types of cis-trans isomerization reactions is that in case of most of the alkenes, only two lowest absorptions, they involve pi star transition or Rydberg transition, and the two absorptions in case singlet absorption in case of ethylene, they are very close, and they are around 170 kilocalorie per mole of energy is required. Whereas in case of substitutable alkenes, the Rydberg transition is at a lower energy. For example, in case of cis-butene, these are the three values for the three transitions. That is singlet pi star transition, it requires 164 kilocalorie per mole of energy. Then singlet Rydberg transition requires 141 kilocalorie per mole of energy, whereas the triplet pi star transition requires 97 kilocalorie per mole of energy. So the lowest triplet state which has pi star character This requires around 94 to 99 kilocalorie per mole of energy in case of cis-trans isomerization reactions. Then on irradiation, what happens is that say this is the ground state of the alkene molecule. When this is radiated with UV light, then this will be the first Frank-Condon planar state in the first excited state as per Frank-Condon principle. Then this planar excited state, either it can be singlet or it can be triplet. This relaxes by rotation of the terminal group, that is in case of alkenes this is methylene group. In case of unsubstituted alkene it is methylene, and in case of substituted it is substituted methylene group, which is rotated by 90 degree around the central bond to give the lowest energy conformation possible. So this is the lowest energy conformation possible through a rotation of 90 degree of. And this first excited planar state can undergo different types of reactions, photochemical reactions. So either it can undergo rotation through 90 degree and it can relax through twisted state to give us cis-trans isomerization reactions, or it can undergo hydrogen abstraction reactions like dissociation reactions can take place. Then another type of reactions possible is addition to other alkenes can take place. First excited state that can interact with other alkenes to give us different types of addition products in case of alkenes. Then this first excited state, first Frank-Condon planar state can also undergo rearrangement reaction. And in this lecture we will discuss mainly cis-trans isomerization reactions. And the cis-trans isomerization reaction, this can take place by two methods. Either direct irradiation of the alkenes can take place, or the products can be formed through sensitization, that is use of sensitizer to give us cis-trans products. Now first the cis-trans isomerization by direct irradiation. As I have told you that because high energy is required for intersystem crossing from singlet state to the triplet state, so direct irradiation reactions, they generally take place in the singlet excited states only, not in the triplet excited states. So direct irradiation of simple alkenes which have lambda max less than 200 nanometer, as I have told, is difficult to achieve due to high energy absorptions which are required. However, in case of substituted alkenes where lambda max is more than 200 nanometers, the direct irradiation can give us cis-trans isomerization products very easily, and they can be conveniently drawn into a mixture of cis and trans products. And most common example of direct cis-trans isomerization is given by still beams. So this is the structure for cis still beam. It absorbs at lambda max 284 nanometers, whereas trans absorbs around 300 nanometers. The direct radiation, as I have told you, in case of still beam is done at 330 nanometer, when direct radiation of either cis or trans still beam is done at this wavelength, then we will get a mixture where we will have 93% of the cis product and 7% of the trans product, which will be present in the mixture of this cis-trans isomers. and we can see that the ratio of the products formed at this particular wavelength is constant. It never changes with time, irrespective of how much time we irradiate the reaction mixture. Then such a condition where the ratio of the products remains constant in a photochemical reaction is called as photostationary state. So at 300 nanometer, when we will get a mixture of still beams where 93% of the product is having cis configuration and 7% is having trans configuration, that state will be called as photostationary state in case of still beams. And at photostationary state, the rate of transformation of cis into trans and trans into cis becomes equal. That is why this ratio becomes constant. And the composition at the photostationary state is determined by the extinction coefficient of the two isomers at the exciting wavelength. So in this case, at 330 nanometer, we will measure the extinction coefficient for both the isomers, trans as well as cis isomer. So Emax trans is always greater than Emax cis. So that is why in an equilibrium mixture, more reactants of trans than cis isomer, they will reach the excited state. And because more trans isomers they will reach the excited state, that means more of trans they will undergo rapid relaxation to S0 state. And that is why the product formed is having more cis product, that is 93%, because relaxation in case of cis will be less as compared to trans. Then we can also explain this on the basis of this energy level diagram. Say with respect to dihedral angle, we know in case of cis isomers the dihedral angle is 0 degree, whereas in case of trans it is 180 degree. So when from the ground state the electron is excited to the first excited state, there is a barrier for rotation, that is 62 kilocalorie per mole of energy is required for conversion of cis into trans or trans into cis. And if you see when the angle is 90 degree, then this type of transition state comes into place, and this bonding is absent in case of pi star excited state. So through rotation of the carbon-carbon double bond, in the excited state the bond length of the double bond will increase by about 4.5%. So based on this diagram, we can tell that 7% of the trans isomer will be formed and 93% of the cis isomer will be formed in the photochemical reaction. Then in case of still beams, the mechanism can be like this, that suppose we start with cis still beam, and in case of when this is irradiated with UV light, then this is the singlet planar excited state, and then this will relax through 90 degree to this transition state, that is relaxed transition state, which can lead to the formation of trans product. Similarly, if we start with the trans, this will have this type of planar trans singlet state, and this by absorption of 2 kilocalorie per mole of energy can be converted into a relaxed transition state of this type, which can then give us the cis isomer. So this is how, through this relaxed transition state, we can have a mixture of cis and trans stilbenes, and at a given photostationary state there will be a fixed ratio of formation of these cis and trans isomers. And as I have told you that trans stilbenes, they absorb more light at the exciting wavelength, therefore extinction coefficient for the trans isomer is always greater than the extinction coefficient of the cis isomer. For example, in case of stilbene, the value is 16,300 in case of extinction coefficient of trans isomer, whereas extinction coefficient of cis isomer has the value of 2880, and this leads to almost complete conversion of a more stable trans isomer to a less stable cis isomer in case of stilbenes. So the synthetic utility of these cis-trans isomerization reaction is that through these isomerizations we can synthesize less stable alkenes from more stable alkenes. So these are some of the examples where trans stilbene is converted into more stable trans alkenes. They can be converted into less stable cis alkenes. So this is phenyl methyl ethene. This can be converted into cis isomer. Similarly, these types of cinnamic acids or substituted cinnamic acids from trans configurations, they can be converted into cis configurations. Then these types of substituted alkenes from trans to cis isomer, they can be converted. Similarly, the alkenes containing heterocyclic rings can also be converted from trans to cis through these cis-trans isomerization reactions by direct irradiation of UV light. Then second method of cis-trans isomerization is through sensitization. As I have told you that the energy required for intersystem crossing in case of alkenes is very high, and because of that direct irradiation is sometimes not possible, and under those conditions we can use some sensitizer which can convert a singlet excited state into a triplet excited state through intersystem crossing. So what the procedure for this is, when the sensitizer is irradiated, then it is excited to the first excited state, and because this sensitizer can easily undergo intersystem crossing, this will change into a triplet state. Then sensitizer in the triplet state will interact with the substrate molecule, that is say transalkene, and this will transfer its energy to the transalkene, and this will become excited, and the sensitizer will come to its ground state, and this excited alkene molecule then undergo relaxation through rotation, and we will get this type of relaxed triplet state, and this will get converted into the other isomer, that is less stable cis alkene will be formed through sensitization. So this is the mechanism how we can get cis-trans isomerization reactions through sensitization. And most commonly used sensitizer molecules, they are ketones. Then this can be explained on the basis of this diagram also, energy level diagram. We know that alkene substrate from singlet ground state, it will change into singlet first exciter state, and this intersystem crossing is a slow process in case of alkene substrate because the energy required for this intersystem crossing is very high. So what happens is we radiate sensitizer, and this sensitizer changes into singlet first exciter state, which through a very fast reaction is converted through intersystem crossing is converted into a triplet state, and in the triplet state the sensitizer collides with the substrate molecule, that is alkene. R is our substrate molecule, and through this collision the alkene substrate will become excited, and this excited alkene molecule then undergo relaxation and gets converted into less stable alkene, that is cis alkene is formed from the trans alkene. So this is the process of sensitization in case of cis-trans isomerization reactions. Now these are some of the commonly used sensitizers. Benzophenone is most commonly used, and the energy required for intersystem crossing in triplet energy is 69 kilocalories per mole, and when this much of energy is transferred, then the cis-trans ratio of the products formed is 60 to 40%. Then if we use benzyl as the sensitizer, then this much of triplet energy is required, and this is the ratio 85 to 15. 85% of cis product is formed and 15% of trans product is formed, and this ratio is in the photostationary state, that is the final at a given wavelength in case of use of these as the sensitizer. Then pyrene can also be used. This much of energy, 47 kilocalorie per mole of energy is required, and ratio of the product formed is 90 to 10. So cis is formed in 90% and trans is formed in 10%. And when eosine is used, then only trans alkene is there, no cis alkene is formed when eosine is used as the sensitizer. Then we can also use halogens for these cis-trans isomerization reactions, and here the mechanism is slightly different. Here we can say that halogen will act as a sensitizer. The halogen will when these halogens, they undergo photochemical irradiation, they are converted into halogen free radicals, and then this halogen free radical interacts with the alkene molecule, and when this will add, free radical will add to this carbon-carbon double bond, then these two types of free radicals, they can be formed, and these two types of radicals then can give you at equilibrium a mixture of cis and trans products, where the ratio of these products will be constant at the photostationary state. So this is how any either cis or trans alkene can be converted into a mixture of cis and trans products through cis-trans isomerization by sensitization in the presence of halogens. So these are the references which have been used for preparing this lecture. Thank you very much.